Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to look at probabilistic scheduling. We will be primarily looking at PERT as a method of probabilistic scheduling, but we will also cover some broader aspects of how do you include probability and uncertainty into schedules. The outline of the lecture is as follows. We will first look at uncertainty in general and in project schedules, then go to the PERT, the background and assumptions for PERT. We will go through a stepwise procedure to do PERT, and then go on to an example, and then we will finally summarize. So when we start dealing with uncertainty in projects, it's quite an issue. Now, to be able to know this lecture, one of the prerequisites we are assuming that you are aware of will be as to how to use a normal curve, the probability of an area for a given value, as well as find a value of a given probability. So these exercises with a normal curve you should be able to do. Now, if you are not familiar with this, I would recommend there are several sources on the web. I have listed a few sources here, but this is something which you should be familiar with, because a lot of these operations are required in PERT. Now, if we take uncertainty in projects, okay, we have so far covered the critical path method, and as we are aware, it cannot actually model any probabilistic events. We do everything assuming that it is deterministic, the values for duration there's no uncertainty involved. We are assuming that that's the duration that is going to happen, and we go ahead with the plans. But we certainly realize that in our control that's not what's happening, and we certainly take care of uncertainty more in the monitoring and control part of CPM. But there's no direct way in which we can model uncertainty. But we know that uncertainty is the inherent characteristic of all projects. Not only do we have duration uncertainty, but there's cost, quality, everything. So a challenge of project management is that we have to face uncertainty. And when we take construction projects, we generally say that construction projects have less uncertainty compared to projects like research, defense, space, which are novel projects. The first time somebody is doing something, it's much more difficult to manage the uncertainty on these open-ended projects as in construction. So techniques like for uncertainty modeling are much more prevalent in these research or defense projects rather than construction. But of late, tools for modeling uncertainty have started coming into construction management practice, and we will talk a little bit about this in the introductory slides. So when we look at uncertainty in construction, there's a whole area of risk analysis and management. Okay, so this is now a core area in construction project management, and any good construction project has a risk analysis approach, a risk management approach, and people will quantify and try to manage the risks at all phases of the project. So this is something which is a science on its own, and it's the practice is becoming very popular, but it's beyond the scope of this particular lecture to cover this aspect. But we will certainly look at risk from what PERT can associate it with. Okay, and when we then go into this from the broader perspective of risk analysis and management, when we talk about just duration uncertainty, this itself is one of the biggest risks in the project. The fact that it can exceed the planned duration, or the fact that an activity takes more time than it's supposed to, or how do we actually handle this. So the whole aspect of duration, planning for duration uncertainty, is also a very, very critical part of project planning and control. And PERT was actually developed to handle this. Okay, so primarily they talk about cost and duration uncertainty as the objective of PERT, and PERT explicitly models the uncertainty due to duration. Now, when we are going to estimate uncertainty of the duration, we certainly have to first estimate the activity duration itself, and then how do we actually, we covered this in the earlier lectures as to how we estimate activity duration, but now it's not just a duration we have to estimate, but the uncertainty associated with the duration also. This certainly turns out to be a challenge. When we go back, you might be familiar with this slide. We did this in the initial lectures. We took activity duration estimation, and we had several tools and techniques as specified by the Project Management Institute and the Project Management Body of Knowledge. So we had so two which I have highlighted here are expert judgment or heuristic and the 3-point estimate. We actually covered a parametric estimate as the part of the lecture series earlier. But these tools and techniques have been identified formally, and when we start coming into uncertainty, we certainly have more challenges, as we discussed, and expert judgment is one of the key ways. The other key way is actually to use data. So when we look at probabilistic duration, we need actually a distribution. Okay, we need a probabilistic distribution, and this is how we account for uncertainty in the activity. Now, duration of an activity can be assumed to follow a stochastic variable, okay, and if you look at if I have historical data, I could fit it to some of the distributions you see below. Okay, a lot of times construction follows the beta distribution. You will be hearing more about this. We are all familiar with the normal distribution here, okay, but we will have to play quite a bit of role in the normal distribution also in PERT, and we will see this at a later stage. So I can get historical data and fit it into a distribution, or I can get an opinion from an expert and also try to generate the distribution from it. So obviously when I get an expert opinion, I will have more limited data, but I still should be able to make a reasonable distribution out of it which suits that purpose for which I am applying it to. If we take historical data, so we have what I have given here is a table. So how would I collect historical data? Actually what we would take is, let's say as an activity, and you can see the number of occurrences of a particular duration that activity has undergone. So the activity has been done in as short as 2 days and as long as 19 days, and this is really the frequency of occurrence of the various days. So you can see that on one instance it was done in 2 days, in one instance 3 days, on 5 instances 4 days, 10 instances 5 days, in 8 instances it took 6 days, and so on. Now so this is basically my historical data. Okay, now I can do my statistics, my basic central tendency statistic on this, and I get the mean of this is 8.17 days, the mode is 5 days, and the median is 7 days. Now if I was going to use this as a critical path method, I wanted a single deterministic duration, and I'm going to take the mean, I might take a mean duration, or we might say no, the mode is also a possible duration I could use. Well, so this is something which has to be discussed, and might be finally you need an expert judgment to be able to bring this into it if I'm going to use a single duration. But how do we take this and try to fit a distribution to this? This is what we would ideally want to do if historical data was available. So I could make a frequency plot of this, okay, and then convert the frequency plot into a probability distribution or a cumulative probability distribution as shown here, and from this basically I would need to do some curve fitting, or some statistical data fitting, and a distribution fit should be found. So here you can see the steps I am going through. I get my frequency, I get my probabilistic fit, and I have a range of distributions I could possibly fit this profile into. And the challenge of distribution fitting is to find which of these distributions models my data appropriately. And people have done this for construction projects and generally found that the beta type distribution is best for construction. So you can see some familiar distributions here, there's beta, there's exponential, normal, triangular. So all of these, but actually what I need to do is to be able to take my data and try to do the distribution fit and find which distribution fits my data. And basically, like I said, the beta is what people have found to be good for construction activity duration. Now this would be nice to be able to do this, but certainly there is an overhead when we try to do it from a data perspective. So the other option is to go with an expert estimate. So in this particular case, I get an expert, and I cannot get this level of data from an expert. I cannot get this level of data from an expert, but I will be able to at least get 3 times, saying what is an optimistic time, what's a likely time, what's a pessimistic time, and based on this, again there are several distributions. I mean, I could use a triangular distribution here too, but again what we will find is that a beta distribution has been used to model this kind of expert estimate also. So we are able to now either get data to make the estimate or an expert to make the estimate, and in both cases we ideally need a distribution to be able to model the uncertainty with that information. So if I compare what a deterministic duration versus a probabilistic duration, here I have my network. In my critical path method, you'll recall that I had deterministic values. So this was A was 5 days, B was 4, C was 6, D was 3, and we fixed it at that. Whereas when we come to the probabilistic approach, A now does not have a value of 5, but it has a distribution that is going to define its duration. Similarly, B has another distribution that will define its duration. Here I have basically shown the symbol of a duration. This does not mean that A, B, C, D all have the same distribution. I have just shown an icon for a distribution to say that A, B, C, D will all have a distribution to model the duration. Now, so there is no particular value, no specific. A can take a range of values based on the distribution it specifies, and sampling the distribution at each instance might be giving a different value for the duration of A, which is what actually happens in reality. Every time I repeat A, it will not take exactly the same time of 5 days, but it will change based on some conditions, and if I am able to capture the distribution characteristic and represent the distribution correctly, I have actually captured the uncertainty of the duration of A and represented it appropriately. Now once I have this kind of a representation for my activity durations, there are 2 approaches which are typically used. One is either a simulation approach or a PERT approach. Let us briefly cover the simulation approach because it is getting more and more important today. In a simulation approach, what we would do is we would take those durations and we would run the network several times. So I would run 1, 2, 3 as I have shown. Each time I will take a different sample of value from the distribution. So I will not get a single value. For every run will have a different value. So you will see that I will do several runs in my simulation, and the project will be, it will be like doing the project n number of times. Each time my sample value for each duration will be different, so my project duration will be different. And finally, if I take the samples of all the project durations, I will get a distribution of project duration itself. So that then defines what my project duration characteristics are and the variability in the project duration characteristics. So this is an important area, which is becoming more relevant today. But we are now going to, after this introduction, I am not going to take too much of time, but we are not able to do this because sometimes historical data is not easily available, and this is a problem. If I want to do a fit and a simulation, I am not able to get historical data for it. But even when historical data is available, I might not be able to map my specific project to that kind of data. Okay, so might be I have excavation data for several projects, but the project I am working on is a lot of excavation, but it's not really, that data doesn't suit my type of project. So going through a fit will not make it any better. Now in the 50s, when PERT was developed, people knew about simulation. They would have liked to use simulation, but simulation is computing intensive, and the mainframe of the 1950s had its limitations in being able to compute so many possibilities as we saw here. So they really wanted to go in for a much more closed form kind of an approach, which PERT is. And but now today computing has come out of the limitations that we had in the 50s, and more and more simulation is becoming a very popular approach. Most of the tools, the popular scheduling tools we use, whether it's MF Project or Primavera, will have a simulation engine also to be able to model the uncertainty and risk, but it is not widely practiced. Only some of the leading companies are starting to use simulation based schedules for uncertainty modeling and risk analysis, primarily because getting data is challenging. You could go with expert data and simulation also, but again the simulation technique is also quite a bit more complex than the CPM, and as we discussed, CPM itself is, people are finding it a challenge, to use it properly. So it is going to take some more time before simulation becomes mainstream in our construction projects.